Hello, everyone. My name is Scott. I'm an instructor at the University of South Florida. This is Discrete Math here on the 20th of April. Today we're going to be talking about the halting problem. Chat as usual in Discord and link to this beautiful stream, which I did not provide to the people that are in Discord yet. Let me fix that. So, as I said, chat as usual in Discord, and there is the link to the chat sorry, there's the link to the feed in Discord. Okay. So there's been some issues. Some people are saying they can't hear me. According to the system, people can hear me fine. If you can't hear me, please refresh your browser. Please check your volume. Is there anyone else that cannot hear me? Okay. So today we're going to be talking about the halting problem. This is the last really big topic for the entire class. This is what we've been building up to when we're building up to recursion. Recursion, of course, being useful in and of itself. But today what we want to do is use recursion to show that there are things that if my system can do recursion, which Turing machines can, which computers can, that means that there are problems that I cannot compute. Beyond just the fact that there are things that I cannot enumerate and count. Okay, there are also countable things, and even, things that should be computable that you cannot. This is section, there's a good question. This is section, let me pull it up in the book. I had a bookmark in there. I hope I still have my bookmark because my bookmark is where my notes are. Oh, this is good. I lost my notes as well. Here they are. This is section 6.4, Boolean algebras, Russell's paradox, and the halting problem. Okay. Of course, we're not going to cover Boolean algebras. That's cool, but it's beyond the scope of this course. If you were computer science majors are, of course, covering it. What we want is we want an intuitive understanding of the basic halting problem for this. And what we want is to talk about why recursion is important for this. And then we want to talk about Godel's incompleteness theorem. Okay. Next time, I wanted to cover more about regular expressions. Next time, I'm going to cover at least the beginning of what a regular expression is because they're extremely important in IT, and there are things that you can't do with regular expressions. I want to talk about that. That may take 2 classes, and if it does, that's the end of the course. If it doesn't take 2 classes, after introducing regular expressions, I will talk a little bit about P versus NP and why that's important to us. If we don't make it, I'm sorry. That's stuff I'm sorry to see go, but it has to go. Okay, are there any questions other than that? Okay, so let's look at the quiz. You all just took a quiz, and it would help if I had the menu option to go to the quizzes. Okay, so you had a chunk of code, and this code is a recursive function. Okay, so what happens here? I come in and I have a large string of ifs. Okay, if n is greater than 0, I'm going to move 2 towards 0, so I'm going to subtract 2. If n is less than 0, I'm going to move 2 towards 0, which means I'm going to go to plus in the other direction. And if I'm at 0, then I'm done. And I return. Okay? So 1 to 5, how do we feel about this piece of code? What it's going to do? Okay. I guess I'll type in the poll. No, it's not a while loop. You can do it with a while loop, but the point is this I'm going to do recursively. Okay? So I'm going to do this using recursion instead of using a while loop. Okay. So let's see what happens. This is just an example. Let's see what happens. What happened to my screen? It's Windows. It does strange things. Why did it do that? Let's try this again. There we go. So I take this piece of code, shown here, and what I'm going to do here is right here, what I've done is I've basically added the thing so that I can add an argument. So instead of having move towards 0, 6 at the bottom here, I'm going to make it so that I have an argument. So whatever I input is going to be the thing. And I will post this code. You can look at this code. This is very helpful in your scripts, right? So what I'm going to do is I'm going to ask it move towards 0, 8. And if I execute this code, it's going to, go to 8. It's going to, okay, so it starts with n, and it's going to call itself again, but this time with 6, n minus 2. I'm not there yet. It prints that, and it was called with 6, and I'm going to call with 4. Then I'm going to call with 2, and then I'm going to call with 0, and when it calls with 0, it's going to say now with 0 and be done. So my question was that if I start with, I think, 6, let me pull back up my question. How many times would the script display not there yet? Well, it started with 6. It printed not there yet and went minus 2. Then it took 4, said not there yet and went minus 2. Then it took 2, said not there yet, and then subtracted 2. And then finally it got to 0. And then it was done. So how many times did it call move towards 0? Well, 1, 2, 3. How do we feel about that? 1 to 5. Okay. Of course, if I start with -8, it's going to be adding 2 each time. All right, so I did -8, -2, I'm sorry, -8 plus 2, -6 plus 2, -4 plus 2, -2, and so I went 4 times. How do we feel about that one, 1 to 5? So we're doing the little negative. Okay. Well, now comes the thing that's kind of tricky. Now I'm going to ask it an odd number. I'm going to ask it 11. And watch what happens. Okay? Yes, that's right. In order to make this stop doing this, I had to actually hit Control-C. I had to actually terminate the command. Let's do it again, but this time I'll hit Control-C right away and see if I can capture the beginning of the command. Nope, not fast enough. Way not fast enough. Let's try it again. Okay, well, I wanted to do the very beginning. Okay, well, there's no way for me apparently to be fast enough to do this. I would have to change the code so that it only did so many. Okay, but what's the point? The point is that it goes 11, 9, 7, 5, 3, 1, and then it goes to -1, and then it goes to +1, and then it goes to -1, and then it goes to +1, and it never stops. So how do we feel about this, that it would never stop? 1 to 5. Right? It's stuck in an infinite loop. Okay. And remember, when I say the word never stops, I mean that, if we left this thing running till the end of the universe, it would still be going. All right. When I say never, I mean it in a very strong sense. Okay. Are there any questions about this problem? Okay. So that was the big idea behind recursion. So the question is, why do I care? So let's go over it. So today what we want to go over is something called the halting problem. And these are the three big giants. I've got Turing, Godel, and Church. Church, for some reason, his picture is not going to cooperate and put his dates where they should be. Not that Church is smaller than these other two, but, let's just make it wide up. Okay, so we got Turing, Godel, and Church. And in order to talk about this problem, we need to talk about what a compiler is. So when I think about functions, and by the way, if your head does not hurt at the end of this thing, okay, then you didn't listen well enough and you need to rewatch it because your head should hurt while you're doing this, okay? This is weird. It's important, but it's weird. Okay, so what's a compiler? Anyone have a good definition of a compiler for me? Or just a so-so good definition of compiler? Right. It's a program that translates algorithm. Did I spell it? Oh, yes. Well, no. I did spell it right when I said it before. I'm not in the computer science department, and I'm really not in the English department. It's a program that translates algorithms into machine code. For our purposes, that's enough. I don't know what this thing is doing. It was doing this before. Okay, good. It's back. If this thing keeps happening, what's going to happen is I'm going to have to wing it on the thing because this was happening this morning and it's getting worse now. Anyway, so so let's give an example, right? So GCC, I've got the C compiler. So here's hello world written in C. Is everyone on board with this? This is the C. Now, PHP is not a compiled language. Neither, well, Java can be or can't be. Java compiles into something called bytecode, which then has an interpreter, or a virtual machine that runs on it, which is basically an interpreter. Or you can compile it into machine code using a Java compiler, as opposed to the bytecode compiler. But C is kind of the standard, code thing that I compile with, okay? So let's take this lovely little program here. This is machine out. Now, the computer can't run this straight, right? It doesn't have, well, it could if it had an interpreter, but it's not meant to be. It's not like PHP, which is meant to do this. So, there's hello world CC. So I start up GCC and I do hello world.c and I hit enter. And then when I hit ls again, I get this a.out because I didn't specify what I wanted my output file to be. It just did a.out. So now, however, I run this as a program, And this is actually in machine code. So if I do less a dot out, right, it's going to give me gobbledygook because it's not text, it's machine code. All right, are we all on board with this? So what this program did was it took my text and it created machine code. And so if I do this, but if I run the program, I get what I wanted. Hello world. Okay? So how do we feel about what a compiler does? How do we feel about what a compiler does? I get gobbledygook. Okay. Now, here's the important bit. The important thing is that I can compile my compiler. In other words, right, the GCC takes code as input. It can take its own code as input. In other words, I can run GCC of GCC. Okay? And this is called self-hosting. Okay. How do we feel about that 1 to 5? This idea that this function can call itself the algorithm for itself, right? This function can take the function not as its own input. So in other words, I take GCC, the code for it written in C, and I compile it using GCC. And that's also what a the GNU C compiler. This thing, right? It is its own compiler. Okay? And if you want to, you can actually look at it. So if I go to Git, so this is the GNU's Git, okay? And I can actually see the source code. So let's see. Here's the tree. I've got all the permissions that go into it. And then I've got all of these little libraries, right? libcc. These are all written. These are header files. But the point is that the program itself is written in C, along with some other things. But it's mostly written in C. You know, it's got some assembly in there and stuff like that. And it can be used to compile itself. So I compile a version of GNU-CC, and then I use that version to compile the next version. But at some point, right, I can also just use it to call itself. So for instance, I want to compile a new Linux kernel. I can use Linux and GCC running on top of Linux to compile a new Linux kernel. In other words, it's self-hosting. I can call GCC on GCC itself. Okay? And that's weird. Okay? And GCC stands for the GNU C compiler. Okay? So how do we feel 1 to 5 about this idea that that a function can call its own code? In a sense, there exists functions like compilers that can call themselves, that can accept themselves as input, right? So I usually think of a function as taking something as input, and that function can be, this is different from a recursive function, which kept calling itself. Now I'm calling myself as the data. Okay? My input for the function is the data. How do we feel about that? 1 to 5. This is not recursion yet. All I'm saying is that I can this idea that a function can call itself as data. And you see this a lot in Java when you do certain types of injections. And in JavaScript, it's all over ECMAScript. Oh my goodness, where you have procedures and then you have them call other procedures as input. So it's a little weird. This idea, PHP sort of supports it, but not really. Okay. So what does this have to do with the halting problem? Theorem. And this is Turing, Godel, Church, a bunch of other people. So this, whether or not, which one's the problem, right? It depends which version of the theorem you call it. There exist there exist problems that are uncomputable. Okay, that I can't write algorithms to do. Okay, proof. Okay, so we'll do this as another theorem. The halting problem. Let's just say here. Okay, so can I have a general function that detects whether a certain piece of code given a certain piece of data with halt. Okay, that's the halting problem. Now, for example, today during on the quiz, you had this problem here, right? Here was your algorithm, right? This move towards 0. Now, if I gave this moves to 0, if I fed the algorithm moves to 0 4, the function would halt. Whereas if I fed it any odd number, the function would not. Okay? So, let's say that this function exists. I would call it check halt. Okay? So let's suppose that such a function did exist, and I call it check halt. Now, the thing's struggling to keep up, and I'm sorry about the lag, but the internet, I'm looking at the bars right now, and it's going, and there's nothing I can do. Okay. So, well, I can, except that if I do it now, it's going to cause the whole thing to freeze by the time I'm done. All right. Okay. So now, if I fed this function, so if I ran check halt on move towards 0, comma 8, is it going to sync check halt for me, or did I just mess it up by writing on this one and that one at the same time? Only time will tell. Let's hold on. Ah, there it goes. So if I run check halt on move towards 0, 8, what's it going to return? Okay, so this algorithm excuse me, it's thinking about working. It's still thinking about working. Okay, it's not working. Okay, so it returns true if algorithm A hearts with data D and false otherwise. All right, is everyone on board with what this function does? So 1 to 5, oops, let's move towards 0. So 1 to 5, how do we feel about what this function does? If it existed. It reads the algorithm and reads the input data and tells me whether or not I'm going to wind up in an infinite loop. And now it's got 2 8s there. It still returned the same thing. I don't know why it decided 2 8s was appropriate. But it did. Okay. So if I ran it with that data, sorry, I just hit the mic with my phone, with my hand. If I ran it with that data, so check halt would return true, whereas if I gave it an odd number, okay, so how do we feel about that? Right? If I ran it with one thing, I'd get, if I ran it with an even number, I wind up with true. And if I run it with an odd number, I run up with false. Because if I give it an odd number, it's never going to halt. Okay? Okay. All right. Okay. So let's suppose such a function exists. Theorem. It's still failing. All right, let's go to plan B here. And plan B will necessitate the use of plan C at some point because the internet's stupid right now. I need OBS. OBS, OBS, OBS. All right, let's see if I can make this work. Okay. So, okay. Suppose otherwise. Suppose such a function does exist. Okay? Now, well, if such a function did exist, right, and remember this check function takes as its input an algorithm and a piece of data. That's the data that goes in, an algorithm and a piece of data. Okay? So how do we feel about what's happened so far? 1 to 5. Again, it's not. So how do we, oops, come on. How do we feel about this 1 to 5? Okay. I'm going to suppose that such a function does exist. Okay. Now, I'm going to let A be a function Okay. It's now, it's not letting me write anymore. Let A be a function that's kind of like a compiler. Let A be a function that can take its own code as input. Okay? How do we feel about that? So, how do we feel about that? Okay, I've taken a function that's like a compiler and used it I've taken some function that looks like a compiler, something that could take its own code as input, an algorithm that could take itself as input. Okay? And now I'm going to run check halt AA. Right, now I can run check halt AA. And it will return true if A would, it returns true if A would halt given A. I love this. Every time it fails to write, I sit here doing this, right? I'm like, I shake the pen like it's ink, right? Come on, Marie. No, it's not going to work that way. Returns true if A of A halts and false otherwise. So, how do we feel about that little bit of setup, 1 to 5? Okay. All right. Well, now I'm going to create a new function. And your book calls it test, so I will call it test. And test does as follows. Normally in the literature it's called G. Your book decided to call it test. I don't know why, but we're going to call it test. And test does the following. Test looks like this. Where did I write it down? So now I'm going to create a new algorithm. Test is the following algorithm. So test takes algorithms as input, and it looks like the following. I even emphasize that. Empty loop. Okay? That's test. Test is nothing but an empty loop. It's a while loop that keeps running. So, how do we feel about that piece of this 1 to 5? This is the idea that what I've written is a new function that will keep running forever as long as check halt returns true. Right? So, if check halt AA returns true, test runs an infinite loop. Okay? So it's going to input an algorithm as its input. Now I'm going to run test of test. Okay, and here's the kicker. Okay, if check halt test test is true, in other words, if test halts, if test of test halts, what does test of test return? If test test halts, then what does test do? So if this thing runs forever, okay, that implies that test test was false and it halted. However, if check halt just as I'm getting to the punchline. I know. I know it's flickering. Just as I got to the punchline, it started flickering again. However, if test is false, then what happened? If test loops forever, then test halted, implying check halt test is true. This is absurd. And I've come to a contradiction. Okay. So how do we feel about that? 1 to 5. And are there any questions? There should be 1,000 questions. If your head doesn't hurt, I either did a really, really, really good job teaching it, and I mean a better job teaching it than any other teacher I've ever seen teach it in the world, or you don't understand it, in which case I didn't do a very good job. You know, either the presentation was or you guys were brilliant, which is, you know, also possible. You, you guys are much smarter than me because this thing makes my head hurt. Okay. So I wasn't testing anything with test. Okay. So if you're going back to test even, okay? If I'm going way back up here to test even, okay? That would keep looping. It's not so much I'm testing. I hate this word. I hate this function named test. But your book used test, so I thought it was important to use test. Test is the special function that halts if check halt AA is true. I'm sorry, is false. And it doesn't halt if check halt AA was true. Okay? And it doesn't really, I hate the word, the name test, but that's the one the book used that I felt obligated to use it. You can use G as the example if you want to. The standard is to call it G, but the book called it this, so I was using this. Okay. All right. Okay, anyone want to take bets on plan B working for any length of time? No, there cannot be a program that okay, so when you hit Alt Control Delete on your computer, what happens? Okay. So if I come up here and I hit Alt Control Delete, what's going to happen? Well, everyone's going to see me, my computer go Task Manager and black screen. Okay? And then the Task Manager comes up. And the Task Manager tells me that this is running. I've got an instance of team running. I've got 3 messages on my teams. I've got OBS Studio running. I've got OneNote running. I've got Photos running. Why is Photos running? I don't know why Photos is running. I've got the PDF thing running. We'll get rid of it. And then I've got, AccuTray, all the Adobe stuff running in the background. Okay? Now, all these programs are running. Okay, so is everyone on board with that? Now, what this theorem tells me is that when this thing goes, and if I started up Skyrim, it would say not responding. Okay? Because Skyrim is sitting there in a loop, loading itself. Okay? But then, eventually, this not responding would go away. Okay? But the computer can't tell if a program is stuck in an infinite loop. That's the point. I can't actually check it if the computer is stuck in an infinite loop. Okay? Because it may finish what it's processing. The computer cannot tell the difference between stuck in an infinite loop and I've just got a lot of calculations to do. In other words, the computer cannot tell the difference in general. It can in specific instances, but the computer cannot tell the difference between this and this. The computer cannot tell the difference between me asking it a really, 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 really big number okay? The computer cannot tell the difference between this and this. Okay? That's the implication of this thing. It cannot tell the difference about that. It cannot tell the difference whether or not. Now, sometimes you can't. You can write things that check for loopings in the. You can approximate it somehow. Sometimes, right? So, like chess. Okay. Does anyone know that there's a rule in chess that says if the same 3 rules get repeated, if the same set of moves get repeated, the same board configurations happen 3 times, the same sequence of board configurations happen 3 times, that the game's a tie. Okay? And that's the thing that the computer can check. The computer can't actually check to see if there's a way to break out of this loop or if the loop will eventually terminate. But the computer can do things like detect whether or not you've repeated X number of times. Right? So I can compute whether or not I've run the exact same memory configuration 10 times or whatever. But I can't tell that the algorithm is eventually going to break out. And that's the point. How do we feel about that 1 to 5? And that's the big piece here. So 1 to 5, we're probably going to end the class by crashing my computer, yes, but because it overheats or runs out of battery. Oops, I need a 5 pole. So 1 to 5, how do we feel about this? It's weird. And as I said, if your head doesn't hurt, you don't really understand it yet. Or I'm just really, really good, which is possible. Okay. Okay. So let's move on here a little bit. Okay. Now let's see if this thing works. All right, it's up. Okay. So let's see if I get another 10 minutes. We got another 10. I'm sorry, we got another 15 minutes left in class. Okay, so let's see if I can get this computer to work. Well, Godel's incompleteness theorem. We're not going to prove it, but the proof is very similar, except I have to get around the fact that I'm using dicts. Godel's incompleteness thing. Math is a little bit more powerful, right? I can't enumerate over a computer can't enumerate over something that's bigger than a countable set. But in mathematics, we have things called times finite induction and stuff like this. So I actually can, under circumstances, certain circumstances, do things that talk about things that are bigger than infinity, or bigger than countable infinity, bigger than the natural numbers. Okay. But there's something called Gödel's incompleteness theorem, and it's the same basic idea. So Gödel's incompleteness theorem says that any mathematical system capable of induction, okay, in other words, any system capable of recursion, because remember they're the exact same thing, has statements that can be proven neither true or false. Okay, there are statements that cannot be proven. Oh, and one of these. So, at the risk of sending you back to high school geometry flashbacks, at the risk of invoking high school geometry flashbacks, does everyone remember this idea that I have a sequence of axioms for geometry? I have things like two parallel lines can never touch. Between any 2 points, there exists one and only one line that passes between both points. Right? Everyone remember these systems of high school geometry? Well, if I have a system of mathematics, right? If I have axioms, right? Yes, that says axioms. So if I have such a system of axioms, okay, I cannot prove whether or not those axioms are consistent using the axioms themselves, as long as my system is powerful enough um, to do induction. As long as my system is capable of doing piano arithmetic, which is the technical term for it, my system, I cannot prove using my axioms that my axioms are consistent. In other words, all of math is built on sand. We're pretty sure about it, but this is where mathematics has to go off and tell philosophy, okay, you have a job now, right? You talk about these things philosophically because we can't actually prove they are consistent. And it's important to note that the system has come crashing down on us twice. So the entire system came crashing down when people started doing non-Euclidean geometries, and then the entire system came crashing down when Russell stated Russell's paradox. Are there any other questions about this? Okay. Any questions, comments, issues, suggestions, thoughts? Okay. So the first thing is that there is homework. So there is homework on WebAssign that is due Tuesday, so tomorrow. And the other piece of homework is this. Google or look up Okay. So I want you to create, I want you to look up regular expressions, and I want you to find a regular expression that would match the string A, B, B, A, B, 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 A, but not B, A, B, B, A. Okay. So you're going to need things like terminators and wildcards or counts or things like that. Are there any questions, comments, issues, suggestions, and thoughts? Okay. So today what we did was we finished up recursion on the quiz review. We went over the halting problem, the existence of incomputable problems, and Godel's incompleteness theorem. We talked about compilers, the halting problem, and Godel's incompleteness theorem. The next time we're going to start with regular expressions. Now, the regular expression isn't really an assignment. It's something I'm telling you to do for next time. Okay? So maybe there'll be a quiz question, maybe not. But it'll be something that'll ask you like, okay, find a regular expression that matches this, but not this. Okay? And that's what I want you to do for next time. So basically, I'm asking you to look up stuff for next time. Are there any other questions, comments? Okay. There's no homework. Okay, it's not to be turned in unless I ask for it on a quiz. Okay? Are there any other questions? This is work I want you to do at home, but not necessarily for credit. Okay. Don't forget to fill out the course evaluation. Everyone should have gotten it. I looked at the thing, and there's only like 40% people that have filled it out. So please get on the course evaluation and fill it out. I don't want you to lose the extra point. That's it for me. I will get into Discord chat now, and I will answer questions there.